but I do want to do a quick poll before the presentation. So how many of you use the LinkedIn search or other search systems today? Raise your hands. A lot, yeah. And how many of you had a bad search experience? Typically, you didn't find what you want. Also, many people, right? Many people, great, okay. So, yeah, that's why we have this talk. Okay, so many times when we search, we just want to quickly get things, get what we want. And we hope the search system can be very smart enough to understand what we ask, and smart enough to even read our mind. So, which comes to the processing of natural language data that is appearing almost everywhere in a system, in search systems. And this leading to our topic today, how to leverage deep learning for natural language processing in search systems. My name is Huiji. I am an engineer manager for the AI Algorithm Foundation team at LinkedIn. Today, we are going to present to you the deep natural language processing in search systems. And this is a joint presentation with Weiwei Guo and Xiaowei Liu. So where are these natural language data in search systems? Let's take a look at it. We have user, right? User send a query to our search systems, and the search system try to fetch data from a large pool of database. A database may contain many kinds of documents, could be job posts, member profiles, course descriptions, or news articles. And then return top K, most relevant results to the user with certain ranking algorithms. And sometimes you also want to do personalization, so we make sure like user have different search experience based on their preference. Now, where are the natural language data? Member profile, right? This is the example of member profile. It's my member profile. So we have like a industry, experience, or education. On the doc side, we also have many kinds of text data. For example, course description, job posts, or news articles. Yeah. Now, query itself, most of the time, it is also a text data, natural language text data. So together, we have natural language data here. And as we just mentioned, as you can see, it is appearing everywhere in search systems. Now, the problem is this is a very critical process to understand, to process natural language data for search quality improvement. Right. So, but it is not quite clear where are these natural language processing technology can be leveraged to different search components, because we have very complicated search ecosystems. So, and how to design these algorithms to improve these components? This is also a question. These are all down to understanding the search ecosystem first. Now, we again starting with a query. Now, what's next? Usually, search system could have some kind of natural language generation for search assistant. And this search assistant could cover a set of components. For example, anyone can come up with an example. What kind of search component is providing this kind of assistance to the user? Anything here? I've had it, yes, great. Give you a hint, autocomplete, yes, type ahead. What else? Ranking, we'll talk about, yes, we'll talk about ranking later, yeah. Here is for natural language generation. So we have spell check. What would be anything else? Query instructions or query expansions. Right? There are also many things. I think for ranking, there are also some special requirements if we can generate something for that. But here we only list a set of representative tasks. Now, come back to the left part, natural language generation. What's next? We want to understand that, right? Understand the natural languages. And this also corresponding to a set of tasks, including text processing, query understanding, and document understanding. On the text processing side, it usually covers some fundamental technologies or fundamental tasks like language detection, tokenization. Then for the query understanding side, it also covers some typical tasks. Another quiz here, what would be a query understanding task? Passing, yeah, passing the query. For example, query tagging. Want to extract the entities from the query by passing the information will be as query intent. Right? When user come to a search system, you can imagine he come to complete some tasks. He may want to find a people or find a newsletter or just want to pick up some kind of knowledge. These are different tasks, different intentions. If we can understand these intentions, it will be very helpful for us to do the further ranking and personalization. Yeah. The third part is for the document understanding, and this is usually helpful for indexing and the query document matching. And these last two tasks is also referring to the retrieval and ranking, which complete our search ecosystem. I think it's quite clear here where natural language processing is behavior and which kind of search components it is related to. But is it easy to do natural language processing in search systems? It has challenges, right? What kind of challenges do we have? First is the data ambiguity. Data ambiguity comes from many places. One is from the short text. Query usually is short. Now here's an example, ABC. If someone type ABC as a query, you can imagine it could be the ABC news, ABC store, right? If you go to Hawaii, you will see so many ABC stores, or what kind of ABC companies. This is one type of ambiguity. The second one, from the non-restricted syntax. Here's another example. Imagine you have a query, Bing search engineer. Now, one interpretation, it could be looking for engineers from the Bing search. And there could be another interpretation. What it could be? Sorry, what you say? That could be another one, yeah. And there's also another one. It could be a search engine engineer whose name is Bing. Could be one, right? So this is all because there's no strict syntax. Yeah. And another one has strong correlations to the searcher. The query has strong correlation to the searcher. This is also something sometimes causing ambiguity. For example, a query looking for new jobs. Somehow, apparently, this should be a job seeker looking for new jobs, right? We should return job posts. But can you think about another interpretation? It could be, oh, you mentioned recruiter. Yes, it could be recruiter looking for candidates whose headline is looking for new jobs. The second challenge comes from the deep semantics. So in search systems, matching is a big problem. How can we match query and documents? This relies on to have a good representation on both sides. And this will regarding how to learn a good feature space for both query and documentation with respect to their search intent, topics, and entities. One example here is if someone search for engineering openings, the system should understand that this is looking for job posts, for jobs, yeah, and specifically to engineer jobs. Now, so these are the traditional challenges for natural language processing in search systems, and it is quite straightforward, or making people exciting to think about. Deep learning can be applied here, right? Because deep learning is famous for its good representation learning and to get a higher and informative abstract layer on different entities or word embeddings, and also in the meanwhile to address ambiguity. So applying deep learning to natural language processing in such system seems a good idea, but it still comes with challenges. First challenge is because such system is very complicated. So there are many components correlated to each other from upstream to downstream. For example, if we want to design a query suggestion algorithm, it will affect both the recall and the precision in downstream retrieval and ranking. If you want to do a query tagging, try to extract the entities from the query, you can think about it needs to be compatible with downstream retrieval, because if you do retrieval, it may need some information from the tagging entities, and as well as the ranking if it is used as a feature. Right. The second challenge is from the product requirement, so product-oriented model design. developing a deep learning model in such system is not as easy as training an offline model. So many times it needs to consider the product special product request. Yeah, and it also needs to consider something happened after you deliver the model. For example, there are lots of business rules, post-filter results or blending or user experience you need to consider when you design the model. But we know deep learning model is very bad on the model understanding, on model interpretation. How can we handle these things, right? Of course, model understanding is another topic, also very hard, right? That's why we need that. So these are the challenges. We need to design product-oriented model. Last one is the online latency. This is a monster. When you develop deep learning models, always think about whether we can solve it. And many times, we have to sacrifice the offline performance, relevance performance, in order to accommodate the online latency. Okay, so but assume we can address these challenges. Now we apply deep learning to natural language processing in such systems. And typically, there are two ways. First way, we can do feature-driven. For example, let's do representation learning. We try to learn some features from the data with deep learning models, like a word embedding, sentence embedding, or kind of embedding. Use that as a feature to plug it into the existing model, which may not be a deep learning model, and may be because of the latency concern. As a model could be like a linear model, logistic regression, or ensemble model like the boosting tree models. That's one way. Second way, we can do model-driven. We can directly learn a deep learning model and use that to power the product feature. Two typical ways. But in this talk, we are only going to cover one way. Which way are we going to cover? Take a guess. Think about which one is more challenging. In my opinion, model-driven is more challenging. That's why we are going to talk about that. Okay, so we have been talking about natural language data and applications, challenges, but we haven't talked about what is natural language processing. Fundamentally, from a technology perspective, what is natural language processing? Natural language is a sequence of words. So processing natural language is to process a sequence. Now, this has alternative word to describe this thing. You have a question? Okay. Oh, you have a question? Okay, yeah. So sequential modeling is a word. And along the sequential modeling, we have identified a set of tasks here. For example, from a sequence to another sequence. This could be a sequence-to-sequence problem. And the typical product feature could be query extraction, query expansion. Another direction is to look at from a partial sequence to a completed sequence. This is usually correlated to a product feature called autocomplete. Basically, you have something, you type some word and you want to complete it. And the typical technology could be ASTM-based language modeling. These two corresponding to the natural language generation. The third one could be from a sequence to a label. This is a typical classification task, right? And there's also some kind of search components can be addressed, can be improved by this kind of algorithm. One thing is called query intention. We also mentioned this before. And another task is from a sequence to a word labels, a set of word labels. And these word labels, it's not just like a multi-class classification. It is correlated labels. So typical application could be entity recognition, like query tagger, or entity tagging for documents. So sequential tagging is usually fundamental technologies in this area. And the last one, what is the last one? Ranking. Important component from sequence to documents. Neural ranker is the fifth task that completes this picture. So overall, in this talk, we are going to dive into details of each of the components to talk about how deep learning is used for natural language processing in search systems. And with that, I will hand the presentation to Wei Wei, who is going to give the first exciting component illustration on the autocomplete, which belongs to the natural language processing generation category. Yeah. Thank you.
Thank you. Can everyone hear me? Okay. So I'm also in the AI algorithm foundation team. So me and my teammate will go over the 5 representative tasks in the search systems. So there are 5 tasks here, and the first 2 are natural language generation task, the autocomplete and the query suggestion, and the other 3 are natural language understanding task. So let's start with the first one, autocomplete. So I believe everyone has used autocomplete before. So just one caveat. So the definition of the autocomplete is give a prefix, you need to predict the completed query rather than just predicting the completed word. So in this example, the prefix is SOFTW. So the completed word is software, but apparently the users are much more interested in the software engineer salary. So you should complete the query. You should suggest the first query rather than the third one. So there are several challenges in autocomplete. The first one is it is probably the product that has the highest requirement of latency. So therefore, currently in the search system, the autocomplete system, the autocomplete component is designed to be very simple because it has to execute very fast. And then we also notice that the traditional method cannot encode very powerful features based on how the query looks like. Usually we found that the most helpful textual features is just the query frequency. So with 2 challenges in mind, our design is a 2-step approach. We generate the candidate first, and then we rank it once. So for candidate generation, it's based on the search query log. We collect the query frequency, and then we use something called FST to construct a try structure. So it can returns the most frequent completed queries for any prefix in a very short time. So some details is that if the prefix is never seen, then we remove one word. And then from the beginning, for example, if the query prefix is metamine SOF, because the metamine is rarely seen in the query log. So we remove that and then we complete the query based on the SOF. For candidate ranking, here's how we use the deep neural network for the NLP. We use the neural language model as the scoring function. So this is how the neural language model works. For a query like that contains 2 words, W1 and W2, we inserted a special token, which is called start of the sentence. We run an LSTM over it. And this is the language modeling part. For each the hidden state, we will try to predict the next word. So basically, it's a softmax over the vocabulary. Assume we have 30K vocabulary, then you can think of the language model as the 30,000K ways of classification. And then the score of the query is simply the sum of the probability of each word. So we have done some optimization in terms of the algorithm part, and we are able to achieve 6 times speed up in order to ramp it online. So we have done some offline experiment on the public dataset, and the baseline is the most popular candidate, which is directly the output of the FST. And also we do some backoff, which means that if the prefix is not seen, the first word is get rid of. And the evaluation is mean reciprocal rank. if the correct query is ranked at the 4th place, then we get a score of 0.25. And we can see here, by using the neural language model, we are able to improve both of the baseline by a large margin. Okay, I'll hand over to my teammate.
Thanks, everyone. So my name is Xiaowei. I'm also from the AI Algorithms Foundation team. And so in the following component, I'll talk about the query suggestion, which is another like sequence-to-sequence model that that's actually in our production. So so what is query suggestion? So if you if you go to LinkedIn and then you search for something, and then you will probably see a list of queries that are like people also search for. So for example, here, someone searched for senior software engineer, and then basically we will give you a list of queries that we think are related. And so for example, senior software engineer, those type of queries. So so how could we tackle this problem? So traditional way of doing this is just based on frequency. So we can collect query pairs. For example, you will have software and then software engineer as query pairs, and then we can collect these from the search logs. And basically, we can save the frequent pairs in a key value store and then just serve it online. And so an obvious limitation for this is just lack of generalization. So by using a purely string matching approach, we definitely cannot handle unseen queries, as well as we cannot handle rare words. So maybe we can take a step back and then just think of how we can better do this to solve the query suggestion problem. So if you think of when users search for something, and we actually, in the query suggestion, we want to mimic the process of the query reformulation. So for example, if you search for software engineer and then you think, maybe I should search for software engineer at LinkedIn, and then you reformulated your query and searched again. So this is actually a very important feature, and we actually want to develop a model to mimic that. So that's actually our inspiration. So we want to use like a sequence-to-sequence model to capture the user's query reformulation. And here comes the fun part. So this is basically the model architecture of sequence-to-sequence model. So we approach this model with two different parts. First one is the encoder, and then second one is the decoder. So for encoder, basically we will have the input as the first query in the query pair. So in this case, we have LinkedIn engineering. And basically that, you can think of the embedding of these tokens are fed into an LSTM layer. And through the LSTM layer, we get the last hidden state output of that LSTM layer to be actually the encoder representation, which hopefully contains all of the sequential information that are embedded in the first query. And then using that information together with the second query, because during training, the second query is also given. So using these information in the decoder, we actually want to kind of produce the next word. Or you can think of it as the next token at each position. So for example, at the very first position, we just have to start like an identifier, and then we actually want to predict the token LinkedIn. And then at the second position, we actually want to produce the token software. So basically, what we are trying to do here is trying to sort of generate the target sequence or the target query that we can use as the related search queries. So we can simply compute the probability of the target sequence as the product of each of the probability of these tokens appearing at relevant position. So that's what we're trying to maximize. And then during inference, what's going to happen is that we don't really have the second query because that's obvious. We are trying to sort of produce that. So basically, the encoder part is kind of similar to what we talked about previously. You have LinkedIn engineering as input, and then going through the LSTM layer. After we get the output from the LSTM, we will produce the first token as LinkedIn. And then after that, we'll use that token as the input to the next position, and then try to generate another token in a sequential way until we hit a special token that's the end of sequence. So that's pretty much how we do the decoding in sort of like a greedy search way. So basically at each position, you're just trying to get the word with the maximum probability at that time. But this can cause some problem because you can accumulate small errors, and then these small errors may get bigger and bigger as you sequentially predict. So we actually also use beam search. So in short, beam search just give you a couple candidates at each position, and then that way we're able to kind of mitigate the kind of error that greedy search could bring you. So that's pretty much about the algorithm. And obviously with the sequence-to-sequence modeling together with beam search, we encounter problems like the latency could be too long for one query. So how can we solve that? How can we put our model on, to serve as an online production? So basically, we see that for search ranking, we actually have a even larger latency. So actually, by making the query suggestion in parallel with the search ranking, we are able to serve the model online without problem. So we also want to show some online performance here. So for English market, we see a lot of great coverage. We have impression and click-through rates gained. And also similar trends are observed on internationalization market, that's the I-18N. And we see increases in successful searches as well as first order actions. So that's pretty much it about the query suggestion. And then in the next two modules, we're going to talk about the query, actually the natural language understanding tasks, which include the query intention as well as the query tagger. And I'll first talk about the query intention, and then I'll hand over back to Wei Wei to talk about the following components. So what is query intention or query intent on a search engine? So let's say when you go to LinkedIn and you want to search for something, and so basically you're trying to you have a task that you want to finish. For example, I want to search for jobs. I want to search for maybe like people or my colleagues, things like that. So the task is actually trying to understand what user wants to do, what user wants to search for on LinkedIn. So a very interesting or like a very straightforward application would be the search vertical selection. So that's like the query intent we're talking about here. So obviously we have challenges as shown in the picture. So basically the semantics are kind of complicated in the search query or natural languages in general. So for example, when a user search for Steve Jobs, are they looking for jobs or are they just looking for a particular person? So obviously Steve Jobs is a first and last name. It's a person's name. So we want to show user people results. But if you have a query intent that's based on that's using a rule-based approach, obviously you will probably just diverge into jobs results, which is not good. And the second challenge here is that we also want personalization in our search systems. So basically what we mean by that is, So for example, we have the same query, LinkedIn Analytics, searched by two different users. One may be a job seeker, the other one may be a recruiter. So they probably will have different intent, even though they're searching for the same query. So basically for job seekers, we want to provide them with more jobs results. And then for a recruiter, mainly they can be just looking for people. So we want to show them more people results. So that's probably the most challenging parts of this system. And then we're gonna kind of talk about what architecture or algorithm we used for building the query intention model. So as we shown on this slide, we use a CNN-based approach. That's kind of like a text classification algorithm that tries to solve the query intention prediction. So we can take a detailed look. So at the very beginning, we have the sequence of tokens. That's just a searched query. So in this case, it's LinkedIn software engineer position. And so after we have this sequence of tokens, we figure out their embeddings. We have an embedding layer that's like the input layer to the following convolution layers. So by doing convolution that's in a one-dimensional manner, which is actually the convolution along the time or the sequence dimension, we are trying to capture the word, the semantic features inside the text. And by using different height of filters, we can actually hopefully capture the word n-grams patterns. So that's what we do here. So after the convolution layers, we have max pooling corresponding to each layer. And then basically at this point, we extracted the semantics features of the query side. And how about personalization? So we also want personalization. So basically we also concatenated the member level features to the query side features, and then together fed into a dense layer. And after that, it's basically just different search verticals. So that we have here, we may have more labels in different applications, but this will just be a softmax among different labels. So that's pretty much the model architecture. And we also want to show some offline and online results here. So as we can see, overall accuracy by the CNN model is increased. And we also see an increase in F1 scores on the different search verticals. And then online results also show that we have click-through rates gained or increased across different verticals, as well as the overall clicks and CTRs. So that's pretty much it about query intention. So I'll hand over back to Wei Wei to talk about the query tagging, as well as the following.
Okay, the next product is about query tagger. So for query tagger, different from the classification task, it's all about predict classification for each word. So this is a typical search query, LinkedIn software engineer, data science jobs. So what we are interested in is to identify the entities in it. So for example, the LinkedIn is a company, the software engineer is a job title, the data scientist is another job title. For the keyword jobs, there is no entity in it, so therefore we tag it as O. So one problem with this tagging schema is that we don't know the boundary of the entities. Therefore, people usually use the BIO notation. So B represents the beginning of the entity, and I means inside of the entity. So for example, BT means beginning of a job title, and then IAT means inside of job title. So the most simple way to do that is to apply logistic regression. So you can create a very large sparse feature vector. So the example of the features are like whether the current word is LinkedIn, whether the current word is Facebook, whether the next word is software, whether the next word is LinkedIn. So you can imagine that if we have a vocabulary size of 30K, then the feature size is definitely going to be over 100K. And then based on this very sparse feature vector, you can do n-way classification. N is the number of labels. So one problem with the logistic regression is that the query is actually sequential. So you are sequentially predicting the tag for each word, but you are not using the information of the previous prediction and the next prediction. For example, for the word jobs, if the previous word is predict as a title word, then most likely the jobs is not going to be last name. So therefore, the researchers has developed the conditional random field method. And basically, the whole idea is to make the prediction condition on the left prediction and the right prediction. And the objective function is to find the sequence that has the maximum score. And this is where the deep learning work can be used. So we can simply run an LSTM and then replace the very sparse regional feature vector with the LSTM dense hidden states. So in LinkedIn, actually, we are using semi-Markov CRF. And also, we are experimenting with combining the semi-Markov CRF with deep learning structure. So due to the limited of time, we will not share the result here. The next step is the document ranking, the last task. So this is an example of our help center search vertical. So the words may be too small, so I will read it out. The query is how to hide my profile update. And then because of the keywords, the traditional keyword matching is only based on the surface words exact match. Therefore, the hiding your public profile, which is a wrong article, will be popped out as the second place. So we find that in the help center vertical, people are using very different ways of saying to describe the same problem. Therefore, we decided to take a neural ranking approach. So it all started with a very simple, very traditional two-layer neural network. So you can extract a lot of features from the query document pair, the white features, and then you send it to a hidden layer, and then you compute a score. The kind of features are like cosine similarity or TF, IDF, and or JCAR similarity between the query and document title. And what we can do is to, for any text data, we can apply CNN or even BERT on it to get a text embedding. So we have applied it to the queries, we have applied it to the documents and the searcher's profile, which serves as personalization. And based on that, we generate a lot of deep features. Concatenate with the white features, we can get a more meaningful query document score. So this is only about scoring. So it's about online decoding. And for training, we have another learning to rank layer on top of it. So each cloud or each block here corresponds to a document that, which is the whole picture here. And some of the documents are clicked, some of them are not. And then we have some offline results. We have tested on the people search, which is a very highly optimized search vertical. So by either doing CNN or BERT, we can get significantly better results. And also we have some online results on the help center ranking. The baseline is a very strong baseline CNN, and by simply replacing it with BERT, we are able to get close to double-digit improvement. Okay, that's all for the technical details for the 5 tasks. Some question? Yeah, yeah. Oh. Yeah, it means, so it means beginning of an inside. O is outside. Oh, T means the job title. Oh, okay. Yeah. How big is the what? Oh, training set. It's very big. Yeah, basically we just use the query log. So usually it's like over a million, several million search queries. Huh? Oh, it's not label, it's click-through data.
Frank, it's not labeled. How would you use it?
Oh, it's user click-through data. So we show 10 examples to the user, and the user only click one of them.
So can the user tell you which ones?
Right. Okay. Yeah. It's relatively noisy. Okay.
Go ahead.
Yeah.
Maybe you can just quickly finish.
Okay.
We
yeah,
have some time. We can save the
slide.
Q&A at the very end.
Yeah. So the conclusion, we have done so many experiments, and we found that using deep NLP technology always improve our results. The only caveat is you have to pay attention to the latency. So you have to reach a very good balance between the relevance lift versus the online serving latency. And also, when you design the deep learning NLP technologies, you have to carefully choose the component you want for the specific task. For example, CNN performs better than the classification task, but if your task is cares very much about each word embedding, then LSTM may be a better choice. And lastly, one of our future work is a multilingual model because of the we cannot develop one model for each language. Therefore, it makes much more sense to develop just one model to serve all the languages. Yeah, that's all.
Great, thanks. Let's have a clear question. Okay.
Very, very interesting. You mentioned LSTMs in a few places. Have you thought of using bidirectional LSTMs to see if you can get more meaningful results?
Actually, we did. We in the experiment we actually used bidirectional LSTM. Just a presentation.
I have a question for Xiaowei about the intent. So same question. So like, what's the size of the training set, and do you have to label the training data? Where do you get that?
Well, actually, the answer is also pretty similar. So So for training, actually, so training data collection is actually quite difficult if you're using human labeling. So the approach is also with the click-through query logs. So basically, we let the user tell us what's the label, and then we collected quite a lot of data, like in terms of millions. So yeah. That's actually a good question. So we'll say like for deep learning approach, we actually kind of did several experiments, and then basically this is kind of like the amount of data that's giving us a better result. Yeah. Thanks.
Oh, thank you. Your results is very encouraging. Did I hear it wrong? You said using deep learning model always better than your previous model. Almost always, right? Oh, that's great. That's great. It's totally different experiences for me. Some of our tree models are impossible to beat. But my question is actually related to, I have actually two very brief questions. First is, like you mentioned, word embeddings, right? So do you learn your own word embeddings as one of the end-to-end, like basically word embedding is part of your system, right? Is that true? Like, do you learn word embeddings?
Yeah. So I think word embeddings are come with the deep learning models. So because you can see all the algorithms we presented here is directly using the deep learning model to parse the product feature.
Great.
So you can see the embedding is some kind of side effect we get from the algorithm. Yeah.
Right. So I can understand that. I can understand that because your search probably is very specific related to jobs, and those like relations between words, right? Probably different than other people. So great. Second question is, have you tried attention?
So for example, the sequence-to-sequence modeling and the AST, the BERT, these are all attention-based framework. That's why these are all kind of incorporated in the technology. But we didn't present much details here. Yeah.
So you mentioned that latency is very important. I was curious, do you enforce a maximum latency? And if you do, how do you do it?
We actually do not enforce the maximum latency because different product has different preference. For example, autocomplete usually has a very strict latency, more strict than ranking model. So our design is mainly like a product oriented. So it depends on what kind of latency we can allow. Then we try to do surgeon to our model to accommodate that. Oh, it exists. We do a surgeon. We do a surgeon on the model. So for example, there are several things you can, higher level you can do. For example, you can reduce the dimension. You can reduce, for seeing a model, you can reduce the filters. And you can reduce the word vocabulary. You can use, for example, trigram to get a simpler, more compacted word vocabulary, and then the single word vocabulary. These are some kind of things. Yeah. Yes. Do you have a real plan? Oh, it's taking too long. Yes, that is what we are doing. For example, for autocomplete, it takes him too long, then we have to reduce some of the component, make sure it accommodates to current latency. Say, for example, 1 millisecond. Yeah, these are things. Yeah, that's also interesting thing is because once you do this kind of deep learning models, the more you do, the more painful you feel about the model parameter tuning and the structure learning. So, yeah. So that is also one possible thinking on this kind of solution. So another way is if you can consider, for example, latency is online constraints just as your parameters, as your goal to optimize your structure and optimize your parameter, then you can do everything done by automatically. For example, you train a neural network to learn another neural network.
Hi.
Okay, thank you. It's a great talk. I'm curious, you briefly mentioned about the personalization of for search, and maybe not in the query suggestions, but one difference I see from the other search system, you have the profile and you have the network information of the particular person you are searching. So how do you incorporate that information into your personalization for ranking as well as the query suggestions and so on? If yes, how do you do that?
Do you mean how to do personalization in the ranking system?
Especially based on the profile information of the person, as well as maybe the network information you have about the person.
Yeah, there are several ways to do personalization. Here we are just using the user's profile as features. So because different people has different profiles, and then and those profiles are text data, so we can extract different text embedding from it. There are several ways to do that. You can concatenate the extracted features with the original white features. Oh, for example, when the original white features are 2000, and then you can extract the personalized text embedding as 100 features, and then you just concatenate it, so the total number of features are 2100.
So yeah, several ways you can do. For example, also attention. You can use the personal information to as intensive to the attention part.
So can I ask one more, a little bit further about the number of training sets? For example, it's kind of related with how many different kind of intent that you're trying to do, right? So maybe I cannot ask how many different kind of intent you have, but in average, say you have 100 intent, how many chances you might have? So you have 1,000 intent, you might have, say, you need 1 million. So can you kind of give us some idea what kind? Maybe needed.
I think that's a fair question. So here in the query intent task that we showed, is mainly doing vertical selection. So if you go to LinkedIn, you'll just know how many verticals that we have. So that's kind of like fewer intentions. There's not like hundreds or thousands of intentions. But yeah, if you're doing an intention in a finer granularity, for example, for each vertical, you might also have different intents, then you definitely probably need more data. But I don't have an exact number for that, but I feel, yeah, you definitely have to take into consideration. Yeah. We just found our answer, yeah. Right. I mean, if you reduce the size of your training data, for example, if you reduce it to half, it might not hurt the model performance that bad. Yeah, it's just that, yes, that's how we.
So I think we are almost the time. So let's take the last question if we have. Okay, I'm on the very back.
Thank you. Besides just increasing the size of your training sets, do you use any techniques to increase the representativeness of those training sets?
Can you maybe go into more details?
Yes. So the demographic representativeness of the text that you're using for training sets, there are going to be different dialects that come along with different cultures. Do you use any kind of methods to make sure you're getting an even distribution of those different ways of speaking?
I see. So probably like maybe on different markets, it will probably like a simpler one would be like different languages. Is that kind of by the representative? Do you think that's Yeah, I feel that's definitely something, and we also have the multilingual models that kind of try to deal with these type of difficulties, and to train a different model for different languages will definitely help on the international market.
Great, great. Thanks a lot.